Welcome. In this video we'll be covering differential signals and differential amplifiers. Let's start off by talking about differential signals. So for differential signals, many circuits and systems make use of differential signals. We find that Ethernet uses differential signaling. Serial ATA or SATA uses differential signaling. That's how your SSD is connected on your computer. PCI Express, which is inside your computer, makes use of differential signaling. Memory lines on memory chips make use of differential signaling for the memory lines, and they use sense amplifiers, which are differential. Analog digital converters, digital to analog converters, all generally make use of differential signaling. So what are some of the advantages of a differential signaling? One of the advantages is that it rejects common mode interference. So to see this is probably the main advantage for using them, is if we imagine that we have a voltage V1, it's going to a far node V1 prime. So we have a long wire that's connected here. Let's say there's an interference noise at this point. That's only worry about V1. Let's say this is a noise current coming in. So we can show that the output voltage here, V1 prime, will equal the original voltage, V1, plus, in this case, half the current. Assuming half goes to V1 prime and half goes to V2 prime. So half the current times RS, RS being the source resistance over here. So we have basically, we've ended up at the far end having the original signal plus some noise on it. If we run a separate wire that has the exact same source resistance on it, then what we'll see is that we can write the similar equation for V2 prime, and we'll have this equation down here. So the benefit of this, if you look at these two voltages, that V1 prime and V2 prime both have the same noise portion on them. So assuming that the two wires are symmetrical and the noise is injected similarly between the two sides, then if we look at the difference between V2 prime and V1 prime, we see the original V2 minus V1 with no noise on it. So we've canceled our interference noise. So to make use of this, we send a single signal as V2 minus V1. So rather than using two wires to send two signals, we use two wires just to send one signal. So we use these two wires to send one single signal. So in this case, we can let V2 equal a common mode voltage plus a differential voltage divided by 2. We can then let V1 equal a common mode voltage minus a differential voltage divided by 2. So here we'll see that the differential signal VID will be defined to be V2 minus V1, or the difference between V1 and V2. A common mode signal, V sub Cm, is defined to be the average of the two voltages. So it'd be given as V2 plus V1 divided by 2, which is the average of V1 and V2. So interference noise on a chip might be power supply noise on the chip that is going from the power supply into different parts of the circuit, and if our circuit is differential, then we can reject that power supply noise. It could also be RF noise on an Ethernet cable. A long Ethernet cable could pick up radio frequency noise on it. And so what they do for this is they actually twist the wires inside the cable so that the RF noise becomes matched on both the wires. And that helps to reject, to make the RF noise into a common mode noise and be the same on both wires, and therefore it can be rejected at the far end. The final other advantage of differential signals is that differential signals, say on an Ethernet wire, they also radiate less RF signals. So they have less radiation, and that helps to meet the FCC regulations. The reason they have less radiation is because they're radiating the same, actually they're radiating plus and minus the signals on two adjacent wires right beside each other. So if you move a little bit away from it, that radiated signal is rejected. So in this case, the RF signal becomes the common mode as you move further away from the wire, and that rejects the differential signals. Now let's look at differential amplifiers. So differential amplifiers make use of differential inputs used in op-amps. So a typical op-amp shown on the left here is this one here. This op-amp is a differential input to a single-ended output Vout. On the right-hand side, we have over here a fully differential op-amp. In this case, we have a differential input and a differential output, and so this is considered a fully differential op-amp, and it would actually require some common mode feedback in order to guarantee that the output is also stable. Differential inputs of an op-amp make use of matched transistors. So shown here is a typical two-stage CMOS op-amp. We have our matched differential inputs right here, M1 and M2. So M1 and M2 should be matched, meaning they have the same width over length, and they also would have the same threshold and same UN Cox. And they generally are placed very close to each other on an integrated chip so that they can be better matched. In this case here, the first stage is our differential input, but it converts it to a single-ended output. And then that single-ended output gets further multiplied by a gain stage M6 with a current source load M7 and creates the final output, which is single-ended as well, Vout in this case. The compensation capacitor here, C sub C, is added for stability purposes. So next we want to look at the large signal and small signal operation for MOS differential pair. Here we see a MOS differential pair with resistive load. We have a current source at the bottom driving our differential pair. The differential pair is M1 and M2, shown here. And we're driving this with input voltage VG1 and VG2. As I mentioned before, M1 and M2 are considered to be identical, so that they are matched. They will have the same threshold, same UN Cox, same width over length. And we have a negative power supply here, minus VSS, and a positive power supply here, VDD. So first off, what we know from this circuit is that ID1 plus ID2 must equal the current I sub B. So it must equal this current here. So we have this equation. So it's going to be true, and that will always be true no matter what the voltages are, assuming that I sub B remains in the active region, so there's enough voltage across I sub B so that it can operate properly as a current source. In the case where VG1 equals VG2, so make the two voltages the same, what we have is that the ID1 will equal ID2, and half the current will go in one direction and half the current will go in the other direction. So in other words, this current here will be split equally from here and here. In the case where VG1 becomes higher than VG2, then this current will become larger and this current will become smaller. So more current will go through ID1 and less current will go through ID2. In the opposite case, if we instead increase this one and this one decreases somewhat, then the current through this transistor M2 will be large and the current through this one will be smaller. So we can steer the current one way or the other way. So we can steer this current. So let's first look at the common mode operation for this differential amplifier. With common mode operation, we refer to the fact that the gate voltage of M1 equals the gate voltage of M2, which is set to a single voltage V sub Cm, so our common mode voltage. So we'll tie the two gates together and see what happens as we change this voltage. So what we can do is we can first find the DC bias for VD1 and VD2. What we see first off is due to symmetry they're going to be equal, so VD1 equals VD2. And they're going to be this, the power supply voltage minus the voltage across this resistor. The voltage across that resistor will be IB over 2 times RD. Since IB over 2 will flow in this transistor and IB over 2 will flow in this transistor, since the two gates are the same voltage. So we have that the bias voltage for VD1 and VD2 is just equal to VDD minus IB over 2 times RD. And that assumes that M1 and M2 are active and that the current source IB has a large enough voltage across it so that it still has a current of IB through it. So it remains in the active region. Next, we'd like to look at what is the overdrive voltage for VGS1 for M2 or for M1. So we have that this voltage here is VGS2, which is equal to V overdrive 2 plus VTN. So we know that the V overdrive of 2 equals the V overdrive of 1. If we write down the equation for the drain current, we have that ID1 is mu NCox over 2 times width over length. And because both transistors have the same overdrive voltage, we'll just write it as V overdrive. And this is all squared. This is the equation for the transistor when it's in the active region. And this should all equal IB over 2 because half the current went into M1 and half the current went into M2. So if we solve for the overdrive voltage, we end up with the overdrive voltage is given by this equation here, where this 2 term here has been cancelled with this 2 term here. So this becomes the overdrive voltage for the case when half the current is going into transistor 1 and half the current is going into transistor 2. The next thing we'd like to find is how high can we make VCM here. So we'd like to find VCM max. Well, the maximum we can go for this circuit and still make sure that both all circuits remain, all transistors remain in the active region, is as we increase the voltage on the gate of M2, if it goes more than one threshold above VD2, then M2 will go into the triode region. So in other words, to ensure that M2 does not go into the triode region, we need to keep VD2 not less than one threshold below the gate voltage. So if we write that down, we find that the maximum voltage we can put on the input will be the voltage at the drain of M2 or M1 plus one threshold. So it has to, the gate can go 1 VT above the drain voltage. If it goes higher than that, then transistor M1 or M2, which both of them, will go into the triode region. So that's the maximum voltage we can put on VCM. Now we'd like to find VCM minimum. So the lowest we can go on VCM while keeping this operating properly. As we drop VCM, or the gate voltages of M1 and M2, M1 and M2 will remain in the active region, and Vs will keep dropping. So as this voltage drops, Vs drops as well. But if it ever drops below the voltage that IB requires to maintain itself as a current source, then that is when this current source will leave the active region and go into the triode region. So we can see that that voltage here, the minimum, so VCM minimum, is going to be, start off with the negative supply, so it's going to be this voltage plus this voltage here, which is V sub CS. We're going to find this as V sub CS. Plus the voltage across here, which is the gate to source voltage, which will be VTN plus V overdrive. So we sum these three together, V sub S minus V sub S plus V sub CS plus VTN plus V overdrive. And we end up with the summing these together here, together with minus VSS, and that becomes the minimum voltage we can put on the gate for this differential amplifier, and all transistors remain in the active region. Next, we'd like to look at the large signal operation for this differential amplifier when we have a differential voltage as our input as opposed to a common mode voltage as the input. So in this case now, we'll ground one terminal. We'll set VG2 equal to ground, and we'll apply V sub ID to VG1. So what we see here is that if we make VID much greater than 0, then all of the current I sub B will flow through M1. So this will go to IB, and this will be 0. Because we put our gate to source voltage so high in M1, and as the source voltage here gets higher, it will eventually cause VGS2 to become less than a threshold voltage, and M2 will turn off. And the higher we go, the more VGS2 will become even smaller and will certainly turn off even more. If we go the opposite direction, and we instead let VID be much less than 0, the opposite happens. Instead, in that case, all the current will flow down through M2. So we'd like to know at what voltage for VID does M2 just turn off. So this transistor here just enter into the cutoff region. In other words, VGS2 becomes approximately equal to VTN. So we'd like to know when ID2 is approximately equal to 0, or in other words, when M2 just turns off. So So in this case, when M2 is just turning off, we'll have that VGS2 will equal the threshold voltage of the device, which means that the source voltage here will equal minus VTN, since the gate is equal to ground. So we have at this point here that VS, the source of M2 and M1, will equal minus VTN. Now we know that the gate to source 1 voltage is given by VTN plus the overdrive voltage, and we'll call it overdrive voltage prime here, because in this case here, we're dealing with the case where the current through that transistor is no longer IB over 2, but is now all of the current IB. So we'll call the overdrive voltage VOV prime for the case when the current through the transistor is equal to IB and not IB over 2. In the previous case, V overdrive was equal to the case when the drain current was equal to IB divided by 2. So if you write the equation for this case, we'll have that V overdrive prime is given by this equation. And we can see that that, related to the original V overdrive, is root 2 times higher. And as I mentioned, V overdrive is the case when ID is equal to IB divided by 2, where V overdrive prime is when ID is equal to IB. Now we'd like to find the differential voltage when this occurs. We have that VID is equal to the source voltage plus VGS1. In other words, we have that this voltage here is VS, so this voltage relative to ground. So this voltage relative to ground plus the voltage here. So we have that VS, we just said, was equal to minus VTN in the case where M2 is just turning off. And we just found what VGS1 was, given by this equation. So we can, what we see then is that these two terms cancel out. This term and this term cancel. So we just have that the maximum voltage we can put on this, and it still is steering the current, is equal to root 2 times V overdrive. If you go higher than that value, the current is already in M1, and so it doesn't change anymore. It just stays at always IB. But before this value, it's always still steering a little bit of current more and more towards M1. So we can plot then the value of VID relative to the overdrive voltage versus the current through the transistor relative to the bias current IB. And what we see is that we have, when VID max equals 1.4, then none of the current here, this curve here is the curve for ID2. This curve here is a curve for ID2, whereas this curve here is a curve for ID1. So we see once we reach 1.4 down here, that ID2 goes to 0, and we have increasing it further beyond that makes no difference, and it just stays at 0. And at that point, we also have that ID1 has become all the way to IB. So it becomes exactly IB in this case. And the opposite is happening for ID1. So we can plot both ID1, this curve, and ID2 in this curve. Now you can show, and we're just going to state this without trying to prove it, that the drain current on M1 is given by this equation here. IB2 divided by 2, IB divided by V overdrive times VID over 2, and times this part of the equation here. And a similar equation holds for ID2. So this is just going to be stated and not derived. So this this equation that we have here describes these two curves that we have here. What we see is that they're relatively linear in the region around VID equal to 0, but they become nonlinear as we move further away. So ID has approximately a linear relationship when VID is approximately equal to 0 and becomes nonlinear as ID increases. So when we use it in a small signal operation, we always want to use it around VID is approximately equal to 0. And the further we get away from that, the more nonlinear it's going to become. So next we're going to be looking at the small signal operation of this differential amplifier. For this small signal operation, we'll be applying a common mode plus a differential signal divided by 2 on the gate of M1, and the common mode signal minus the differential signal divided by 2 on the gate of M2. And we'll be looking at the differential output, VOD, so the difference between this terminal subtracting this terminal. And as we've stated before, the bias current will be IB over 2 here and IB over 2 here, because we'll start off assuming VID is equal to 0, in which case we have the gate of M1 equal to the gate of M2, so the bias current splits equally between the two paths. So that becomes our bias condition. So there's really two ways to look at the small signal analysis for a differential amplifier like this. So we'll start off with the first approach here. So this is approach number 1, and just draw out the small signal model as shown. So adding in the small signal models for M1 and M2, so we have the small signal T model for M1 here, and the small signal T model for M2 here. And we're going to assume, in this case, that R0 goes to infinity. So we'll ignore the effect of R0. So if we look at the current, IS1, IS1 is going to be this voltage here, which is VID, divided by this resistance plus this resistance because they're in series. And notice for the current source that we had, which was going to occur down here, we've also assumed its output impedance is infinity, so we've been able to ignore this current source at the bottom here. So what we have then is that IS1 is the differential voltage divided by the series combination of RS1 plus RS2. And if we assume that RS is the same for RS1 and RS2, so we'll just define RS to be the value for that, then it's equal to VID divided by 2 times RS. Now we can look at the output voltage here, VO1, and we can see that that's going to be just this current, IS1, times this resistance. So we have this result here for VO1. Now, we also have that IS2, the current through this resistor, is going to be minus IS1 just by the sign, because this is defined in this direction and this one is defined in this direction. So IS2 is the negative of minus IS1 by definition. So then we put that in, we have that VO2 is equal to minus IS2 times RD, but because IS2 is equal to minus IS1, it's equal to IS1 times RD. So finally, the output differential voltage is VO2 minus VO1. If we subtract those two, we end up with 2 times IS1 times RD. Remember that IS1 is equal to VID divided by 2RS. So we end up with this final result here, that Vout, the differential output resistance, is equal to R sub D, the drain resistance, loads, divided by RS times VID. So we can rewrite this as VOD relative to VID. So the gain of this circuit is given by RD over RS, this term here. And recalling that GM is equal to 1 over RS, it's also equal to just GM times RD. So that's the first way of looking at this circuit. The second way of looking at this circuit, which will give us the same result, is to treat it as a balanced circuit. So say we have a balanced view. So in this case here, we redraw the small signal model, but we assume that we have plus VID over 2 on one side and minus VID over 2 on the other side. So whenever this voltage goes up, this voltage goes down by an equal amount. Now, because they're both being applied across these resistors here, whenever this goes up and this goes down, this voltage remains unchanging. So it remains at 0 volts. So this is a balanced view. This works if everything on the left side is equivalent to everything on the right side. So because we have a balanced circuit here, this holds. And that means, by balance, we mean that RD over here equals this RD, and this transistor on the right side, all the small signal components equal this components for the left-hand side, and that the voltage is truly differential. So really then we just need to find the gain on one side here, and then the other side will have the similar gain. So we know from before, this is just a common source amplifier. So we can think of this as being grounded at this point, since it's always at 0 volts. And then we can write the result that VO1 is just equal to minus RD over RS times VID over 2. So it's just looking at the left-hand side all by itself. Now, we can write similarly that VO2 will equal minus RD over RS times minus VID over 2. If you combine those two, we have that the output differential voltage is VO2 minus VO1 will then be given by this equation, just subtracting this one. Actually, I guess subtracting it the other way, sorry. Subtracting, it's VO2 minus VO1, but there's a negative sign if you here and here that makes this into a positive value, and then we're subtracting VO1 here. So the overall gain becomes GM1 RD times VID, which is the same result that we saw in the previous approach. So let's do an example of a differential amplifier. We'll make use of the balanced approach. So we'll do our analysis on half circuit for this. So we've got this example shown here. If we need to draw a half circuit for this, because everything's symmetrical, if we draw a line right down the middle here, we have nice symmetry. So to draw the half circuit for this, we'll have this circuit down below here, which is the half circuit. So we've assumed that this voltage here is 0, so that becomes the ground node at this point. We've also had to split this resistor of 2K into 1K, because half of it will be shared with the left side and half will be shared with the right side. So in other words, we've just split this resistor and thought of it as two 1K resistors, and this point here becoming 0 volts, because this becomes a V out 2 and V out 1. So one goes up while the other one goes down, so the middle doesn't change. So we take just one side of this, and put it over here. So we can do our analysis on this circuit. We're going to assume, in this case, that V overdrive is equal to 0.2 volts and lambda is equal to 0. If we do the analysis, this should be straightforward for us. We end up that GM is, as usual, is equal to 1 over RS. It's also given by 2 ID divided by V overdrive. ID in this case is going to be IB over 2. So it's 2 times IB over 2 divided by V overdrive. IB was given up above as 1 milliamp. So IB over 2 is 0.5 amps. If you put that all in to the equations, we have that the GM for this circuit is 5 milliamps per volt. And RS then is 1 over GM, which is 200 ohms. Then we can write the gain for this circuit is given by minus V out over 2 relative to VID over 2. So in this circuit here, we're finding the gain from VI over 2 to minus V out of VOD over 2. So the output differential, half of the output differential voltage. If you determine what that gain is, we have from before, it's given by this equation. So the overall gain for this, the 2's in this case, the 2 in this case will cancel out. So the overall gain for this becomes minus 1.67 volts per volt. So I meant to say that the negative V out over VID is equal to minus 1.67 volts per volt. So the actual VOD over VID is just given by positive 1.67 volts per volt in this case. Next, we look at a differential pair with current source loads. So now looking at the case where we have a differential pair with current source loads, we've now added in M3 and M4, which are now PMOS current sources. But we can again treat this as a balanced circuit, so we can just really find the gain on the left-hand side, assuming that this was a ground node. So it's just a single transistor gain cell in this case. And so we have that the gain is going to be given by V out over VID is just the GM of the transistor M1 times the output impedance looking up, so RO3 in parallel with RO1. So we have it's times RO1 in parallel with RO3. We can do a similar thing for a cascaded differential cell, differential gain amplifier. So in this case we have M7 and M5 as cascade current mirror. And again, we can look at the left-hand side only, all by itself. It's a balanced circuit. And we can, from before, we've seen that for a circuit that looks like this, where this is tied to ground, that's a cascade gain cell. We know from before that that gain is given by minus GM1 RON in parallel with ROP, where RON and ROP is shown here. So RON is given by this equation, and ROP is given by this equation. So now we'd like to go back and look at a differential amplifier at a block level again for a second. So if you recall, for a differential amplifier, we have a differential input that results in a differential output. Now the differential input consists of both common mode input, so a common mode in the input, plus a differential on the input. So there's actually two parts to the differential input, the common mode part and the differential input. Similarly, the output has both the common mode output and the differential output. So we define the differential input as being VI1 minus VI2. We also define the differential output as being VO1 minus VO2. But we also now have the common mode input, which is the average of VI1 and VI2. And we have the output common mode output, which is the average of the outputs, VO1 plus VO2 divided by 2. So now we actually have four signals here. The common mode differential input, we have four signals. The input differential signal, the input common mode signal, the output differential signal, and the output common mode signal. So we can actually define four gains through this amplifier. So we have the differential gain, which will be from the input differential to the output differential. That'll be our differential gain. That's always one that we care about. We then also have the common mode to common mode gain. So the input common mode signal to the output common mode signal. So it's a common mode to common mode gain. Generally, that's less of a concern. We also have what's called the common mode to differential gain. So from the input common mode to the output differential. So what we care about is how much, if the common mode is moving, then how much does that change the differential signal? Because that will introduce unwanted differential signal into our system. So that is something to worry about. So that's common mode to differential gain. And then finally, we have the differential to common mode gain. So from the input differential to the output common mode. So we call that A sub D sub Cn. That generally is not that important because normally we're not looking at the output common mode signal. That's not something of interest to us. The output differential signal is. In terms of the common mode to common mode, we generally just want that to be small. So we don't want to amplify our common mode signals. If we have a common mode signal that moves up, we don't want the output common mode to move even higher, and then the next stage even higher than that. So we want to keep our common mode signals not to be amplified. So generally we just want the common mode to common mode gain to be less than 1. So the most important ones though is the differential gain, so the differential input to differential output, and the the common mode input to the differential output. And what we particularly want is that the differential gain is much better, much higher than our common mode to differential gain. So that will reject our noise signals. We don't want our common mode noise because we expect there'll be common mode noise coming in. We don't want that to be converted into differential signals. So we effectively have 4 gains as shown here. As I mentioned, we have our differential to output differential, and that's given by this one. The other one we care about is our input common mode to our output differential, which is also important to us. So we'll end this video here, and in the next video we'll be looking at finding the common mode to differential gain, as well as offset of differential amplifiers and other aspects of differential amplifiers. Thanks for watching.